Hello, my name is Noah Evans. I'm a senior in the Ocean Engineering program at the University of Southern Mississippi. As part of my senior capstone project and honors thesis, I completed a research project on the tuning and performance of PID-controlled low-complexity systems. So to give some context, autonomous underwater vehicles, or AUVs, play key roles in many underwater operations. This includes ocean mapping, reef surveying, and defense reconnaissance. The RoboSub competition challenges students from across the world to build their own AUVs that can complete an obstacle course that replicates tasks that an AUV would have to do in an ocean real-world scenario. One of these tasks is where an AUV must identify a target and shoot torpedoes through it. And so this requires an AUV to have precise control over its position in the water, as even an unintended tilt could cause the torpedo to miss its target. And you can see in the image left that this example of an AUV from the competition is trying to orientate and shoot a torpedo through its target. And you can see the holes for the target are fairly small, so like if the AUV isn't oriented in just the right way, it can miss. So to perform any given task, an AUV must be able to keep steady positions and not lose control. So this is very challenging, as there are 6 degrees of freedom, or DOF, for a fully free-floating AUV to maintain. So degrees of freedom encompass 3 translational movements along an axis. So you have the forward, backwards, you have the right and left, and you have the up and down. And then you have 3 rotational motions about an axis. So you have the pitch, the roll, and the yaw. So you have 3 translational, 3 rotational, and those add up to be 6 total degrees of freedom. And so with so many degrees of freedom to consider, it becomes a challenge of where to begin for a new robotics club that plans to enter the RoboSub competition. But during my robotics internship, we began to build an initial base of knowledge of the instrumentation and methods available to facilitate AUV control. And one method that was investigated was PID control. So proportional integral derivative, or PID controllers, were developed by ocean engineers in the 1920s to automate ship steering. Since then, PID control has spread to be used in a multitude of industries that require automation of a process. This also includes the motion control of AUVs, that's very commonly used. So the PID controllers operate as a closed loop system using 3 terms. You have the proportional term, the integral term, and the derivative term. And these drive the loop towards a goal. The proportional term, this is the proportional term, it responds to the current error, and the integral term responds to the error over time, or the accumulated error, and then the derivative term responds to the rate of error over time. And so each of these terms have gain values, so you have Kp, Ki, Kd, and each of these gain values determine how strong each of the P, I, or D terms are, and these must be tuned for an optimal performance of a system. So tuning these gain values is required for any system to get an ideal response. If you look at the graph right here, you can see that there's an ideal curve in the green where it approaches the set point quickly, but it doesn't overshoot. Perfect response would be like going straight up and you reach the set point without having any sort of overshoot, but that's not physically possible. So the kind of true goal of tuning is to get the ideal curve to get as close or as fast to the set point as possible without overshooting and maintaining that state. If you make the gain values too strong, they can end up overshooting and oscillating, which can be seen in the orange. And if you make the gains too weak, they end up undershooting, and then it takes a really long time to reach your set point. For any system, if you change a small parameter, it would need to be, or a parameter like weight or motor power, the gains of the PID controller would need to be retuned, else you would just be operating with suboptimal gains. And so each PID controller has 3 gains to tune. You can see, if you just look at the roll PID, there's the Kp, Ki, Kd, just for that PID controller. But as the number of degrees of freedom increase, so too does the number of PID controllers to control those degrees. So the control loop that I'm showing currently is a 2 degree of freedom control loop, and it has 2 PID controllers, so it has 6 total gains that need to be tuned. But for like a fully free-floating body that an AUV would be, it has 6 degrees of freedom, so that would be a total of 18 different gains that would need to be tuned. This greatly increases the challenge of tuning, especially when tuning by hand or manual tuning. And so by restricting motion to 1 and 2 degrees of freedom, the process of tuning is simplified and faster to implement. It also aids in the troubleshooting of tuning and testing of PID controllers. Another large factor to consider for PID controller is to determine if the system behaves in a linear manner and if it is fit to be an uncoupled design. So linearity is this mathematical property that just describes how a system behaves. A linear system, or a system, is said to be linear if it follows the principle of superposition, meaning that the total response or the total output is just the sum of individual input. So the behavior can be broken down into these independent parts that can be added together in the end. And if a system is truly linear, it can be, or it justifies the design of a uncoupled design loop. Hold on, there you go. So an uncoupled design loop would computate, or a system is uncoupled when its controller computates its output using only its error signal. So you can kind of see with this controller, I have my two controllers, and the roll PID controller looks at the error for the roll, and then that PID controller looks at the error for the depth. And so this loop design is considered to be uncoupled because the controllers only look at their individual errors. And because of that, they operate and respond independently of one another, even though they both change the actual actuation of the controller. And so for my project goals, I wanted to design two PID controlled systems that restricted motion to 1 and 2 degrees of freedom. 1 degree of freedom for the up and down movement, and then a 2nd degree of freedom for the roll. And even though the roll on this one's kind of oriented in a different manner than what I could call roll, it's still rotating about an axis. I used manual tuning to get the optimal gains for both systems, and because the systems only operate in 1 degree of freedom and 2 degrees of freedom, this is where my title low complexity came in. So tuning and performance of these PID controlled low complexity systems. So just the really simple 1 and 2 degree of freedom designs. Once I had the PID controlled system built, they would be tested for settling time and tracking performance to test the initial hypothesis that increasing the system complexity from 1 to 2 degrees of freedom would decrease performance. The results would then be used to conclude if the system, or if the added degree of roll caused the system to continue behaving in a linear manner, or if it didn't, and then go on to see if a decoupled PID loop design was justified or not. So this is my design approach. The top row indicates my initial design concepts. The goal of the initial design concept was to reduce degrees of freedom to just 1, which would be the vertical depth of the system. So the 4-bar linkage is a parallelogram and ensures that the opposite bar, so this bar and that bar, always remain parallel to each other. And so this is kind of the basis of the 1 degree of freedom design, because I wanted to keep the propeller constantly pointed up and down so that it could just focus on controlling depth. And then by having 2 of these 4-bar linkages side by side, it eliminated any other tilting or swaying motion. The second row depicts my final system designs. And so one of the things I want to do was to match the 2 degree of freedom systems actuator configuration, because it needs 2 motors in order to have this 2 degrees of freedom. I wanted to redesign the 1 degree of freedom system to adopt 2 motors. So in this design, I kept the 4-bar linkage on either side, and it still operates just going up and down, but now it has 2 motors, and this aids in the final comparison between the 2 systems. The 2 degree of freedom system design add the 2nd degree of freedom, where the 1 degree of freedom locks rotational movement. The 2 degree of freedom system allows the motors to swivel about their base and swivel right there, enabling the roll control while also having the up and down movement. The 1 degree of freedom PID control loop uses just a single PID controller for depth. And so the depth PID has a direct impact on motor signals, so that if the depth is below its goal, so like if it's too far down low, it tells the motors to thrust stop. The 2 degree of freedom PID controller uses 2 PID controllers, so roll and depth PID. And the control loop is designed so that the 2 controllers are decoupled from each other. Again, they only look at their own error and they don't take feedback from anything else. And so for this 2 degree of freedom PID control loop, it still functions with the depth the same, where it affects both motors proportionally. But for the roll PID controller, it will take away from one motor and add to another depending on the tilt angle. So like, for instance, right here, for this motor, it will get weakened, and then this motor will get strengthened in order to hopefully level out the controller in the end. Once I had my loops figured out, I began writing programs for each of the systems to facilitate PID control. This loop shown here is a general flow loop that can apply to both systems. I kind of labeled the functions of each as critical or kind of not critical. So the green are critical functions that is absolutely needed for the program to run, but the yellow is kind of, you can maybe take it out if you don't necessarily need it. But it starts by arming the motors and calibrating sensors, and then it kind of stores kind of initial data like the initial tilt angle, the initial depth. And then it begins the super loop in which the timer begins. It starts by checking serial commands, and with the commands I can set different gain values, set which PID controller is active, and set different waveforms for the PID controllers to follow. And then one of the important steps is that it reads the sensors so that it can actually determine the feedback of the depth or the roll, and then calculate how far off it is from the goal, determine the PID response, and then finally send the motor signal, store the previous all the previous data, because the previous data is needed for both the integral and the derivative terms. And then it also plots data so that I can actually read it and determine how it's functioning or how it's working. For the function wave generators, my programs allowed me to set 4 different wave functions. So I have the sinusoidal wave, which is right here, or the sinusoidal, triangular wave, my square wave, and then a sawtooth wave. And I was also able to change the amplitude and periods of these generated wave goals. So you can see on the top, I could make the wave amplitude increase as much as I wanted, well, to the bounds of the tank. And then for the wave period, I could decrease that to get a higher frequency, or vice versa, make the period larger to get a larger or smaller frequency. And then all of this came together whenever I was doing my final testing. From a hardware setup, this general setup applies to both systems because they're set up to be pretty much identical. Both systems use the pressure sensor, which was located between the 2 motors right here, and the pressure sensor was used to get the depth. And then for the 2 degree of freedom system, the IMU was also located in the middle, and it captured the angular velocity and acceleration of the system. And then the ESP32 microcontroller was kind of the brains of it. It read the data from the sensors, it calculated the PID response, and it sent the motor signals through these 2 ESCs, and that went down into both of the motors to generate the thrust. And then I had a power supply unit that provided a steady voltage to both the motors with a 7.4 volts, and then I think it was 3.3 volts to the microcontroller and sensors. One of the unexpected learnings that I had was of electromagnetic interference, where electromagnetic interference is caused when magnetic fields induce a voltage noise inside of some sort of wires. And so for this project, I didn't have any protection for my wires against the EMI that was produced by the brushless motors. And so this led to intermittent communication errors that took a long time to solve and also delayed my tuning and testing of the final project. But the EMI could be mitigated using shielding, which is a conductive material, to engage the sensitive wires and redirect the induced voltage away. So as seen on the left-hand side, I did a kind of makeshift shielding where I wrapped braided copper around my sensitive sensor wires and then connected it to a ground terminal. And you can see the effect in the two images of the oscilloscope. Without the shielding, the voltage signal from my sensor wires is very noisy. But then with the shielding, the induced voltage is directed away, and so the voltage of my sensor wires is a lot cleaner, and I haven't gotten a error or a communication error since. With that error fixed, I was able to begin my tuning. So manual tuning was used to determine the gains, the optimal gains. And manual tuning typically involves an operator using their knowledge to adjust gains, either by doing a procedure and then tweaking gains, or just adjusting gains blindly. For this project, I did a different approach where gains were tested iteratively over a square wave, or slow square wave, so that, and I tracked the error that was generated over these waves to see which gain produced the least amount of error. And you can see to the right, the time for which a gain, or the different gain values were separated on the time that they were operating. And so I took the error that was produced for each of these sections and I put it through a root mean square function to capture the variance of the error. And then the gain that produced the least amount of RMS error was recorded to use for testing. And as you can see for this one, it was a KD of 1. So that was my derivative gain, produced the least amount of error with a value of 1. This method was very particular and took a long time to test and analyze all of it. But the results showed that both systems were very similar. The depth PID gain values were very similar. And so this implies that the system remained linear even after adding the roll. And so this, in a way, supports the decoupled 2-degree freedom PID loop design that you can see here, where, again, the controllers only look at their own error. For my function wave generator, this is what it looks like in operation. So you can just see the dark blue line is the actual wave response, or the goal being set, and then the lighter line is the actual response for the depth. And so what this looks like in practice for my controller is just it going up and down. And this is the following a sinusoidal wave for the depth. And then my wave function generators also work, or they work for depth, but they also work for the roll controller as well. So in this video, it's another sinusoidal wave, but it's instead following, changing the roll, or the goal of the roll. You can see it here. It's following that wave pretty closely. But with this, I could also look at both of them active at the same time. So in this video, I have my depth wave up top, and then my roll wave at the bottom. And so you should see it's going to be tilting side to side while also going up and down at the same time, and it functions fairly smoothly. And so my testing essentially followed these patterns, where I would look at the different waveforms and see how closely I could follow. The main outcomes of my project: tuning was successful, and the results support the assumption that the 2-degree of freedom system's behavior was linear, and that the decoupled PID loop would work and validated. The RMS error as a means of manually finding the gains was effective, but very time consuming. My initial hypothesis that the system would suffer in performance as complexity increased was not successfully supported by any of the testing due to the testing methods showing that both systems operate at essentially the same level. But overall, the complexity of the systems didn't have that much of an impact on performance, just a slight impact, but the linear behavior also seemed to be consistent from 1 degree of freedom to 2 degree of freedom. And then for my budget, I was awarded about $518 from the Eagle Spur grant. The majority was used for equipment, and I'm currently waiting to be reimbursed on travel. The main costs of the budget came from the testing tank, the PETG filament, brushless motors, and the multiple ESCs. So I had to test a few brushless motors and I had to test a few ESCs to see what worked best for my project. And then during this project, I've gained a lot of skills and insight. I developed how well I can troubleshoot issues, manage my time, process data, and find creative solutions, as well as communicate my research to be understood by a wider audience. I developed a lot of hard skills, such as 3D printing and modeling. I advanced my skills in C++ and Arduino, as well as gaining skills like soldering and flashing ESCs. If I were to do this project again, I would start by testing more of the gains during the manual tuning so that I had a wider array of data to look at and draw from. For the settling test, I would choose a larger tolerance so that I didn't have to arbitrarily remove outliers and I could remove any biases I might have had. And for all tests, I would have performed them in the same day whenever my actual systems were working so that I would be able to remove any unknown barriers like maybe temperature or like motor degradation that could have impacted system performance. And then lastly, I found that whenever I got stuck on a issue, I needed to take a wide view to consider all the possible causes and not just try and hone in on one single possible cause and then run down a rabbit hole and get lost for a long time. To wrap this up, I successfully tuned and tested 1 and 2 degree of freedom PID controlled systems. My initial hypothesis wasn't proven, and testing on system complexity will likely need to be expanded upon. I did find that the 1 and 2 degree of freedom systems, in the 1 and 2 degree of freedom systems, behavior seemed to remain fairly linear, which means that in future control loops or PID control designs, they could remain to be decoupled or uncoupled. For future steps, I would recommend creating a dynamic model that could capture all the system parameters to predict system behavior, and then improve the tuning methods like auto tuning or adaptive tuning that would be more consistent and efficient than manual tuning. And then these would also need to make use of the dynamic model that would need to be developed first. Finally, you could extend the PID control to work for all 6 degrees of freedom, but to continue testing for linearity as you extend control. And then finally, when all that's done, you can integrate and test on a fully free-floating vehicle, and then use the modeled system to optimize it and hopefully win the RoboSub competition. And that's it.
Question. Figured it would be mine.
It is way out of my wheelhouse, so I'm just asking a general question.
Well, that's
When you have 2 different PIDs,
yeah.
One for depth, one for
Roll.
Yeah. It's just 2 of 6, right? 6
Right.
degree of freedom.
Right.
Let's say that you have all 6. Then priority is with which one?
I think priority would still remain with depth, because one of the main things is just you need to be able to keep the right altitude in the water, because if you're trying to go through a goal, you don't want to accidentally have to top of the goal, and you don't want to accidentally scrape along the bottom if you're performing a task. And then you need to be able to, like one of the tasks is to find, orient, and pick up objects, and so you need to be able to correctly lower yourself, or the AUV needs to be able to correctly lower itself down into the water, pick up objects, and then find the correct time to drop them. And like, you don't want to accidentally smack into the bottom, because then you break the AUV. And then like for the torpedo test that I talked about, the height is also important, because well, if you're too high or too low, then you also just miss. So that's what I would say is the most important. There's multiple forms to control the height. So lots of people use motors, but there's also like the buoyancy engine that Sam talked about. And I don't know if any AUVs use them in conjunction, but I'm sure it's possible. Yep.
Was this neutrally buoyant?
It was not neutrally buoyant.
So how did you handle, was it buoyant or negative?
It was negatively buoyant. So I'll go back to my initial design. So this initial design was attempted to be negatively or neutrally buoyant. I had a little pressure enclosure on it to have the pressure sensor, and it kind of served as a flotation device. the issue that I ran into with being neutrally buoyant comes with the ESC, the electronic speed controllers. They're used to interpret the signal sent from the microcontroller and spin the motors. So, but on most ESCs, they have what's called a dead band around a certain signal value. And so if you get in that dead band, it just turns off the motor. And so whenever you become neutrally buoyant, your system kind of rises up, and then the microcontroller is like, okay, we're approaching the goal. Let me decrease the strength of the motors, and as it gets to right there, or gets to just about within the goal, or within a certain tolerance of the goal, the motor turns off, and then it falls again. Or if it's too strong, it blows past it, and so it keeps it on a constant set of oscillations. So to just mitigate this, I did opt for a negatively buoyant design because one, it was just easier to work with, and then I did try the positively buoyant design, but then it ended up splashing the line, and it whenever the depth was getting initialized, it made getting depth initialized harder because it didn't go to the bottom successfully every time. Yep.
So now, the heave motion was controlled, right? So there was a certain displacement that you set up and down.
Yeah, the up and down that was the first one that I captured.
How about the roll?
The roll?
Was it also at a certain angle range that you controlled?
How are you talking about the limitations of the angles? Okay, yeah. So the depth controller was, of course, it was limited by my tank value. So like the tank was 300 millimeters or 300 millimeters or 30 centimeters tall. And so with the water in the tank, I could only go up and down about 60 millimeters or 6 centimeters, I think. But for the roll PID and the roll control, the only limitation, or the limitation came in the form of if it went too far to either side, it would actually end up dropping and then trying to overturn itself. And so I did use, let me see, I had sort of a safety precaution with a stopper that prevented over-rotation, and so that kept the wires and the propellers safe for the most part. But even without that, the kind of operational range was kind of plus or minus 60 degrees, 50, 60 degrees before it reached that kind of critical angle and it lost its height and had to go back and regain it.
So about this correction, since it's not a sliding platform,
Correct, yeah.
but a tilting one, as you change the heave, there was an indirect change in sway.
The forward backwards?
Yes.
There was, but that was essentially the arc of the systems was so large that it didn't really come into play. And even then, even if it was to be accounted for, it didn't have an effect on the PID controllers that were being tested, because the forward backward movement that would require motors to be oriented in a sideways manner so that you could actually push forward backwards. And these motors only went up and down, or were meant to be orientated up and down. Yeah.
Following up on Kamal's limitation of your roll motion. If you roll by 90 degrees, I guess you would lose all capability to control your up and down motion, right?
Yes.
Any thoughts of how that would affect your assumption of being a linear system?
Yes. So whenever I was trying to actually find those limits, I did try and push it to its very maximum degrees. And I think I may have misspoke earlier when I said 60 degrees. It may have been 75-ish or 80, because somehow whenever the roll was active, it still kind of pushed up enough that it could maintain some certain depth even at the high angles. But yes, beyond say 80 or 90 degrees, there does seem to be a non-linearity that occurs because
It doesn't, or it does?
the system starts to behave in a non-linear manner because
It is one there.
it starts to have the motors pushing a different direction, and the PID controllers kind of can't account for it trying to push the side instead of just relying on pushing up and down. So it kind of operates within the plus or minus 70, 80 degree range of like, okay, it can orient itself, but whenever it goes beyond that, it acts in a manner that can't kind of be predicted by the controllers. And typically, whenever it did do that, I would have to fix it by hand. So yeah, I would say I didn't release it to behave in a non-linear manner past that. So like in a bunch of the
That's a fairly common thing, that you can only treat systems non-linear for kind of small angles and small deviations from certain
that's what I
zero
was,
positions.
whenever I was researching linearity, that's what I saw. It was like a lot of graphs. It would have like a fairly straight slope, and then it would kind of taper off at the end as you got higher values.
And then for an AUV, you probably never really want to tilt very much because you just zoom off in one direction.
I think the only instance where we would want to spin is when we're going through the entrance of the RoboSub, when you got to spin to get points.
Spin? What do you mean? Or do you get it flipped?
There's a flip. I was looking at the rules, and there was points for, I think it was like 720 degree roll turn or something like that. It seemed like a lot of points to be gained from it.
So the systems they use in the RoboSub, they usually don't rely on just 4 propellers. Right? They have independent propellers for all the different uses.
Yeah, 6
so
or
they
8.
don't run into this issue where
Correct.
you lose all up and down motion with a 90 degree. You do all different systems. Better decoupled than your system.
Was that like that?
They decouple the different degrees of freedom better because they have more actuators.
Yeah, that's the ultimate goal, is to have a completely decoupled design.
Potentially, yeah. And if you're smart enough, you can get away with both propellers. It's just a little more complicated.
Right.
Anybody else? Wesley, what's your question?
I had a question that I actually wanted to ask you. I was going to ask. Did you enjoy this? And if you failed a class, I know you don't have other ones. If you failed a class and stayed, would you enjoy continuing this in different degrees?
Oh. Probably, I would say, as much as I hate to say it because of how long it took and how intensive the project was and how frustrating the project was.
I recall.
But I still feel like I would like to continue it and see it out to the end, because I feel like I set the groundwork out, and I'm like kind of jealous that somebody else gets to continue after.
Yeah.
It's like, I did the hard work. I want to finish.
Well, we're always looking for volunteers to consultants to the RoboSub team.
Oh, there's always teams. Oh yeah, it was.
What if they paid you?
What's it paid, man?
Yeah, like 12.
$20 an hour.
No, like 12 a year, maybe. Yeah, not 1,200. Or 12,000.
It was frustrating at times, especially with that communication error.
You made a lot of progress. I think it'd be cool to see it move into other degrees.
Mm-hmm.
Or it will be cool.
Yeah. What's on that?
I'm not coming back. But I'd like to see it on YouTube or something.
Hey, yeah.
All right.
Did that.